basically of embedded systems. The idea behind it is to have really independent and self-contained modules, language modules, and specific tooling for it, which are not bound to a specific methodology, but which can be freely employed in your environment and which can be integrated into custom tool chains. So all the different modules that we are building are intended to be usable on their own and independent of each other. The basic idea is that they are also open and extendable, so you can easily extend them, customize them. There are two modules that I want to emphasize on today, which are the Statechart tools, and the other one is Damos, which is a modeling tool for block-oriented modeling for dynamic systems, which actually has become an Eclipse project already. They are currently undergoing the IP review process for the source code, so you will still find the code in the Yakindu repository up to now, but it will soon move to Eclipse as well. By the way, my colleague Andreas Unger, who is the project lead there, is going to talk about that tomorrow afternoon, so if you're interested in Damas, you may join there. Today I'm going to talk about the Statechart tools, which are tool set built on Eclipse, open source, that deals with editing Statecharts, with simulation of Statecharts, with, of course, validation of Statecharts, and with the generation of source code from Statecharts. What we regard as a Statechart is similar to what David Harel once defined as his state machine formalism. It's just a little bit different in the sense that as we expect the tooling to be self-contained, we also expect the Statechart formalism that we have to be self-contained. So our Statecharts are actually equipped with an interface. You can see that on the left here. It is specified textually via textual specification language, and it is meant to define the interfaces the Statechart shares with its environment. So that makes our Statechart self-contained, in contrast to, like, for instance, Statecharts, state machines in the UML, which depend on some underlying structural formalism. Here it's not the case. The second thing that makes it a little bit different is that we do not incorporate an event-driven semantics by default, but Yakindu Statecharts have a cycle-based execution semantics. That fits quite well into the embedded domain, where you often find periodically executed Statechart models. So that was an inspiration for Yakindu as well. This cycle-based execution semantics allows us to process concurrent events, because we decouple the execution of the Statechart from the occurrence of events at its interface. And we can easily integrate an event-driven behavior by just defining something, a driver that drives this execution of a Statechart whenever an event occurs at its environment. So the approach is a bit more flexible than what you expect from a classical event-driven Statechart. The time control is fully dedicated to the environment. Even if you see things like after 5 seconds here, that is calculated down to cycles that you can specify within simulation or code generation. So you have full control over the time semantics that it uses there. As I said, we cover editing, simulation, validation, and code generation, and I just want to show you a quick overview over the basic Yakindu Statechart tools. We have editor built on GMF, which has integrated support for textual specification, for the interface of the state machine, for actions or reactions within states, and for the reactions on transitions. And that is based on Xtext, and it is completely integrated into the editor. So if you go into direct editing mode, you have the full support that you expect from an Xtext editor there, like syntax highlighting, like auto-completion, validation, and so on. You also have integrated this Xtext editor in the properties page. You can see that down here. So we have selected the interface specification in the diagram, and we can use Xtext tooling to specify that formally. The editor itself is based on GMF runtime. It's not generated, but it's directly programmed against the GMF runtime. And this separation of textual and graphical aspects we have also incorporated in the underlying meter model. So our meter model is twofold. We have a S-graph meter model which defines the structural aspects of a state machine or a state chart that is defined plainly in EMF, and we have an expression language which is used for the interfaces, for the actions within states, and for the transition effects that is based on an Xtext grammar, which we call S-text. We also have support for simulation of these state charts, and we can simulate them in two ways, either cycle-based or in an event-driven manner. So you can choose that while performing simulation, whether you want to have a cycle-based or an event-based simulation running. Yeah, and we have a simulation view which you can use then to interface into the state chart, so to raise events or to manipulate variables and things like that. Of course, simulation states are properly highlighted as well as transitions. I'll show you that later on in the demo. The interesting thing about our simulation environment is that it doesn't directly simulate the state chart, but that it depends on an intermediate model, which we call SXAC, which is a sequentialized form of the state chart execution. So we calculate all possible execution traces throughout the state chart into a derived model, and the simulation environment runs on that model. The idea behind is that if you want to change the execution semantics, you do not have to adopt or customize our simulation engine, but you simply have to adopt the transformation from sgraph and stext to this intermediate model. Yeah, so it is built for extensibility with this respect. And of course, we also deliver code generators. We have built-in support for Java and C code generators. We're also working on C++ code generators. All these generators can be customized by so-called generator models, which are actually specified in an Xtext language as well, where you basically specify for which state chart you generate code, and by means of so-called features, you can parameterize the code generator. So you can here, for instance, specify the outlet where to generate the code. We also have features that you can specify how code gets inlined or anything else that the generator offers for built-in parameterization, so to say. Of course, all generators are integrated into the Eclipse Builder infrastructure, so you can easily execute them whenever you change your models and have the code regenerated. You can also integrate custom generators quite easily using either the extend2 approach or extend as it is now called, and we also have backwards compatibility support for the old expand language, which is still used in the industrial practice. Interesting thing with the code generators again is that our built-in code generators actually not depend on the state chart formalism itself, but again on this execution model. So if you want to change the execution semantics by manipulating the transformation from the state chart formalism to this execution model, you not only adopt the simulation environment, but you also adopt the code generation basis. So the code generation and the simulation are in sync with respect to the execution semantics there. Okay, I want to give you a short demo and see how that is working live. I just created an M3 simple project, and I will create a state chart, which we call demo, for instance. And it's created with a simple state and an initial state. And let's simply call that state 1. And as I said, our state charts are self-encapsulated and specify an interface. So here I want to specify an interface. We have support for an unnamed default interface, but you can also have named interfaces to group events and variables accordingly. Within the interface, you can specify things like events, operation, variables, and so on. Let's simply create an incoming event here, which we simply call E1. And let's model a transition that is triggered to a new state. Let's call it S2, which actually gets triggered by this event. Here you see the Xtext tooling that gets integrated into the direct editing here. Okay, let's assume we have a second event that's also incoming. And let's assume we want to have a variable that is of type integer. And we can specify an initial value. And let's assume that from this state S2, we want to go back to S1 by means of a time transition. So we use an after trigger here. And let's assume we have an entry action within this state. Let's use this dialog here to specify that. So on entry in this state, we want to increase the counter variable. And let's have a last transition, a self transition here, where we just want to reset this counter variable in terms we receive second event. So if we receive event 1, we want to reset the counter variable. Okay, so this is basically the editing functionality, and let's simulate that Statechart. You get an impression on what can be done from there as well. We can simply run it as a Yakindu Statechart simulation, and then if the screen is large enough, you get such a simulation view. Yes, I can fold in the palette and give you a better look on that. And then you can raise the events, and we have now a cycle-based execution with a specified cycle time. And you see you can inspect the variables. You could also change the value of the variable in place. And of course, we can reset the value as well. This simulation environment has the possibility to change the execution semantics in an event-based manner. And if you have a cycle-based execution, which is the default, you can change the cycle period as well. So you can adopt that to your environment. We also have built-in support for code generators, so we can create a new generator model, and we can specify that we want to do that for this Statechart, and we can specify which of the built-in key Yakindu code generators we want to use. And what gets done then is that we get such a generator model, which basically has support for different features. Here we specify the outlet, and you see the code got directly generated into the source gen folder, which is not created as a source folder. That's the reason why we can't browse the code yet, but I don't think we'll have to do that. You can play with that if you want to yourself. So that's basically what Yakindu offers. As you can download it and as you can execute it as an end user tool, what I want to stress once again is that our tools are based on these different meta models. So the twofold specification of a state machine that is based on the graphical and a textual model, and this intermediate execution model, as well as the generator model to drive the code generators. And when building the Statechart tools, we did that to allow to easily build customized state-based tools. So we built in means for extensibility. So we can, for instance, easily restrict the structural concepts the Statechart offers by dealing with the S-graph model. Or you can customize this textual specification language that is used in the interfaces and the transitions in the states by just customizing that as-text language. You can also adopt the execution semantics by customizing the transformation from the Statechart into this intermediate model, and then you directly have adopted the simulation engine and the code generators. You can, of course, also adopt the built-in code generators. You can extend them with custom ones. We have decoupled the type system. You can also adopt the type system that we use to type event data and variables to your custom type system. Of course, you then have to deal with the certain aspects of simulation and code generation that are related to the type system as well. And of course, you have the possibility to define additional validation constraints. So Yakindu was actually built for extensibility right from the beginning. And now let's come to what I mean with domain-specific Statecharts, because that's what the talk actually is about today. When going into the industry, really noticed that state-based modeling is useful in a lot of domains. But in each of the domain, the Statechart is usually a bit different, and the expression language or the things that are modeled on transitions and the events that are referred to are actually often, you really want to address your domain concepts there, but the formalisms that you normally get if you buy a state-based modeling tool are typically independent of any domain. So our question was, how can we bridge that gap and how can we adopt the Statecharts to really deal with domain concepts? And how can we build a tool or a framework that helps us to easily build up Statechart-based tools that deal with these domain concepts. I give you an example. The domain of human-machine interface modeling, for instance, deals with concepts like scenes or certain widget types like buttons or sliders or labels. And these widgets have certain features that are intrinsic to them. For instance, a scene can be started or stopped, a button can be pressed, a slider can have different values, and so on. And what we really want to do is we want to enhance our Statecharts so we can directly deal with these domain-specific concepts. So we can adopt the state machine to refer to domain-specific context within the declaration of events or within the action code that we use as effects on transitions. For instance, we want to call certain features. We want to express that we want to start the scene when taking a transition in a Statechart. So we want to really integrate the concepts of a particular domain, the HMI domain in this example here. And what we can actually do with Yakindu is that we can exchange this or customize this textual specification language as text to really refer to domain-specific contexts. Here I have a screenshot of a customized Yakindu Statechart where we have incorporated these changes. So here within the action code, for instance, of this entry action in the AC state, we refer to the features that these built-in widget types actually have. So that is direct access to domain-specific concepts there. We also incorporated that into a demo, and I will shortly show that to you. Just very plainly, the domain-specific context, so the different types that are there, the different widget types are defined in a dedicated language that we have built with Xtext, and we have the so-called HMI contract language, which we use to define the configuration of a particular HMI, so of a head unit in this case. So we say we have 4 animations there, we have a fan control in this AC scene, we have 3 sliders, a label, and a couple of buttons. And then within the Statechart, we can really refer to these concepts. So we describe that we want to model a Statechart for a particular head unit. We refer to this application here in the interface. And then within the action code, we can directly access the scenes and the buttons on the widget types that we have. And we have also built in support for simulating that. And we have linked that to a external modeling tool, which is commercial, but which I can show you just for demonstration purposes, where such an HMI is actually modeled. And you can't see that in the details because this resolution here is quite low, but you can see that in the overview in the top right. If I change between different scenes here, for instance, if I go to the AC scene, then the state machine is directly coupled to that, and we can directly simulate that as well here. So if I use the slider here or press the buttons in the left, then you see some state transitions within the state machine. If you have a screen that is large enough, you can easily see that. So just to give you an impression where we customized the tooling, and the effort to do so was not so very large here. So how is it done? If we look below the roof, then as I said, our Statechart formalism is based on two concepts. We have this structural meter model as graph, which defines the structural concepts, which are basically the same for every Statechart formalism. So that defines that you have states, transitions, and so on. And then we have this X-text language, which defines all the declarations for events, for variables, for function that are used in the interface of the Statechart. And we have the expression language that is used for the reaction behavior of the Statechart within the entry and exit action of the states and on the effects of the transitions. And what we can now do is we can exchange or even replace this X-text language with a customized language that refers to concepts that are defined in an external meter model. In our example, it referred to an HMI contract, which defines such a HMI configuration. And we adopted the expression language then to deal with these concepts. And that, of course, can be transferred to different domains and to different concepts. And you can easily use that and build up customized tooling and reuse all the other stuff that is there. So the graphical editor, that would be hard to build, the simulation engine, the code generators. The only thing that you, of course, have to do is you have to adjust the parts that are affected by your change to S-text. So basically the transformation to the intermediate execution model and the type system and so on. And that makes the Statechart then domain-specific and the tooling, of course, as well. And that's basically it. The Yakindu tools are currently hosted at Eclipse Labs. We are planning to have a release candidate within the next weeks, and we want to release by this year and then start with an Eclipse proposal also for the Yakindu Statechart tool. So we want to bring it to Eclipse. If you want to try it out now, you can download it from the Eclipse Lab site, or you can directly go to the Yakindu org project site, which then points you to the Eclipse Lab site where you can find an update site. Actually, the link I've given here is an old one. There's also a UNO update site, of course, available by now. But you can find that, you can find that on the update site. Yeah, so that's it from my side, and I thank you for your attention, and I'm open to questions. Thank you. Any questions? Oh, then I might encourage to try it out, and I wish you a nice coffee break. Well, thank you.